All right. Thanks for joining this next session. We're going to talk about bootable AI containers with Podman Desktop. Whoa, that's a lot of crazy stuff. All right, so we got a lot to cover today, but before we get started, we wanted to talk about this really cool announcement that was made about Red Hat donating all these different container tools to the CNCF. So the tools that we're talking about today are going to be part of that as well, right, Cedric?
Yes, all open source contributions.
Yeah, so bootable containers is one of them, and a bunch of other container tools. So they're all going to go being under the stewardship of the CNCF, and so we're pretty excited about that. And that's also why we're talking about Podman Desktop, because it's also part of that same announcement. So today's schedule, we're going to talk, of course, about bootable containers. What are bootable containers? Who here already has heard of bootable containers, just out of curiosity? Just a few hands, which is great. So we will talk about, what are bootable containers, why they're interesting, and why you should be kind of looking for them. We're going to talk about boot C. We're going to talk about how bootable containers and AI actually are a super cool use case to work together, and we're going to talk about Podman Desktop to make it a little bit easier to work with these tools because it's a really nice user interface. So, quick introduction. Cedric, do you want to go first?
Thanks, Kevin. Yeah, it's an honor to be here with you guys. Hope the conference is going great. I'm an open source engineer and also a developer advocate at Red Hat. And you can primarily find me on YouTube making like little whiteboard videos explaining these concepts. But I also organize, for example, Cloud Native Community Days where I'm from in New York. So if you guys are ever there, highly recommend apply, because the tools that you see today, working with containers and working with bootable containers, are all part of the CNCF ecosystem, right? So it's all part of Kubernetes. And so, yeah, it's an honor to join you, Kevin.
Yeah, thanks. And so I'm Kevin Dubois. I'm a developer advocate at Red Hat. I'm also the technical lead of the CNCF DevX developer experience technical advisory group, and also a Java champion. So Cedric, you're doing more Python these days with AI, but we can actually do a lot of cool stuff with Java as well in AI. But anyway, that's a different talk. All right, so what are bootable containers and what do they solve, right? So that's the big question, because if we kind of take a step back and look at traditional infrastructure and how we manage that, it's usually still kind of a lot of not necessarily manual stuff, right? Most organizations have it automated in some way, but you have these different operating systems that need to go to different footprints. Some of them need to be running on edge devices. Some of them need to run in big data centers. Some of them in virtual machines. And so they all need to be kind of managed differently. You also have different teams, because sometimes they're this kind of Linux system, then they're another Linux system, then they're Windows systems. So how do we manage all that? Because there's going to be like a lot of different ways that we need to configure these and different teams. And then once they're actually running, how do we make sure that there's no drift between these different environments, right? Because if we don't have like a very specific definition of an image that needs to run in a specific footprint, then may well be drift between, we patched these servers on this data center, but we forgot to do those, or so all that kind of management is still very much day-to-day business in a lot of organizations. Now, containers kind of for applications have solved, let's say, a lot of those problems, and containers have this concept of immutable systems where you kind of define ahead, this is what should be in there, this is how it should be configured. And that's what we want to do with our operating systems as well, right? We have these aspirations of having immutable operating systems, and there are some solutions to that, but it's not really that pervasive. But that's really what we want to go to, because then we have knowledge of this is our kind of what we would like it to be, and this is what actually is, and it can be kind of the same, right? So taking a step back to application containers, like I said, where we've kind of solved these kinds of issues, because we had the same issues with application servers and applications in general, right? Where we had these configured and we deploy them to this environment and that environment. We configure them differently. And containers came on as a really cool solution to having a very kind of defined way to package our applications in a standardized way that allowed us to deliver the applications in a standardized way with something like Kubernetes. We also have these registries where we have a standardized way of defining, like with the OCI standardization, how these containers are built, whether you build them with Podman or with Docker or with something else, they're all going to be the same kind of standardized way of packaging. That allows us to have transparency. We can see how these containers are defined with a container file, and then we can have that same kind of portability between different systems.
Right.
And then that allows us to adopt new technologies a lot faster because we can swap different dependencies and rebuild the container image and redeploy it, and it's all automated. So that's beautiful, and that's what we want to do with actual operating systems as well. So with bootable containers, that's kind of the evolution, right? So we have application containers. Most of you, I'm assuming, are familiar with that. So we have a base image, and then we add, our application bits and pieces, maybe some configuration. So with bootable containers, it's kind of the same concept, except now you're actually adding the kernel as part of that container image, allowing you to run this bootable container image on an actual system, started up just the same way that you would install an operating system, but from a container image. So what is a bootable container? It's basically an opinionated way of deploying, configuring, and managing immutable images based on typically Linux systems. So we have that kind of OCI container, the same way that we define container images and the standards for application containers, use the same thing for operating systems. That allows us to use that kind of experience that we've built up over the last decade with container native tooling, best practices, and kind of translate that to the OS and the kernels as well. So we can use that existing tooling and infrastructure to be used to build and ship bootable containers. So let's take a look at how to actually deploy and update systems using this concept. So you start with a Docker file or a container file, whatever you want to call it. So you define just the same way as application containers, right? So you do from something, and then add some files, you copy them, and then from that you build a container image. We're familiar with that. And then we convert that to a disk image that we can then deploy to edge devices, public cloud, virtualization host, bare metal servers, right? So we can use that same kind of concept, the same image to be deployed to these different environments. And then the beauty is really that we then can update those images running on operating systems on the fly, pulling down a new container image that we've built by defining a new kind of, let's say we copied something new into the Docker file, we rebuild the container image, the bootable container image, and then push it to the container registry, and then we'll automatically update the servers because they notice that, oh, there's a new version available, let's roll it out potentially automatically. If you're, wanting to take that automation path, of course. So at the core of bootable containers is bootc, and that's what makes that kind of magic happen once you've deployed your container image to maintain that, right? So it manages the deployed bootc system, performs these updates, so that's what actually pulls down that container image into your operating system and then redeploys it, and then rolls out our container images, our bootable container images. So it allows you to also roll back in case something doesn't go well, and then you can work with systemd timer and services, and it has a stable API, and it integrates with Podman, so it allows you again to have that kind of same experience with containers in very much the same way. So how do you build a bootable container image? As you can see, just like I was saying, it's the same kind of way as you would build regular container images. The only kind of difference here, so you see in the from, from, in this case, Fedora, and you see instead of, using like the usual kind of Fedora base image that you would use for containers, you can see here it's a Fedora boot C base image. So that includes all those bits and pieces to manage the image deployed as an actual system image, and then start that up and run it and package it in that way. And then you can see some run commands to copy some packages, and then copy your potentially your applications or configuration files, and then finally some sort of command to actually start running your image on whatever footprint you deploy it on. So in terms of what kind of distributions are supported for bootable containers, so Fedora, CentOS, and Red Hat Enterprise Linux are kind of our favorites, so that's why we listed them here. But there's many more Linux systems that support bootable containers. So if you're a fan of a different distribution, that's most likely supported as well. And yeah, again,
you could even build your own base image as well, right, on the distribution that you want.
You want to show that? You want to show how it actually is built for, let's say, Fedora?
Let's do it. So I'll hop over here, and this is in the slides here that we've included, and we can show you the link again. But on the documentation page for Fedora, you also have, in addition to Fedora,
I was going to say, make it a little bigger.
Make it a little bigger. Sorry, I know the screen's a little small. But so for Fedora, right, you've got this, base image, and you either have a full image philosophy where you have the kernel, right? You have that command line utility bootc in order to perform those upgrades. You have systemd in order to run your containerized application as a service, network manager, and all of the common utilities here as well. But as we mentioned, you could create your own. So what does that actually look like? Well, I'll head over here to this GitLab for the base image of Fedora. And so here you've got a little bit of documentation on how it works. Specifically, if you want to build your own base image, you can do that with Podman by using this container file here. So you can see what's happening here in this container file is...
Or maybe you can see it if you're in the first row.
Yes, that's fair. We're essentially starting from a base Fedora kind of environment, but then we're using two utilities, so OSTree, as well as rootfs, in order to build a file system specifically to be our base kind of system that we're going to use when we actually build this. But then at the end of the day, we tag it as an OCI container so that we can then use it for our operating systems and deploy it as a system itself. So I think it's pretty cool.
Yeah.
And at the end of the day, and I'll just reload the slides here, at the end of the day, I kind of see it as like, you walk in like a pizzeria, right? You're like, hey, what do you want? Well, I want to start off with, this sauce, and then I want these toppings, and give it to me, and I'll eat it at home. But now we're using it to deploy applications, right?
Yeah. So you're kind of the AI guy, right? So how does this relate to AI workloads? Because this is really cool. We can create these base images. We can create them to run actual operating systems. But we said, we were going to work with AI. So you tell me, how does this relate?
Of course, yeah. I like what you said earlier, the Python guys. So, a lot of these different Python libraries for like PyTorch or different utilities in order to run models such as Llama C++, VLLM, are all kind of in a base of Python. And you kind of have these dependency errors sometimes if you're using a different version, a different dependency of a framework or a kernel. And so this is really perfect for AI/ML stacks. In addition, there's also use cases such as pairing your application with the operating system one-to-one so that you have that all in one container file and you can manage that very transparently. But specifically for AI/ML stacks, which is the topic of the talk today and what you're going to see in the demo, you have the confidence to build these AI applications as system images. And by using containers, this is a really effective way to to work with AI. For example, a lot of us work with NVIDIA NIMs or have heard of them before, which is a good use case of that. But the thing is, having the model as close as possible to the hardware is going to allow for faster inference, for lower latency, and it's going to allow us to build more powerful applications that use RAG or agentic or support MCP. So all of these cool functionalities are improved when we have that model running as close as possible to the hardware. And we actually do this for ourselves at Red Hat with a product that's called Red Hat Enterprise Linux AI. So it's essentially VLLM, in a container. So you can download an open source model and inference it so you have an endpoint for your applications. And so we actually span this into a container file ourselves so that we can version every part of the stack, which is really important to do this at build time versus, hey, let's do this when we're actually running the operating system and doing that into production, because you kind of avoid those pitfalls of, hey, I have one dependency update and it breaks everything. Yeah. So it's a huge opportunity, right?
Right, exactly. And especially for us as developers, this is really nice because somebody can create this container image for me, and I can run it in a virtual machine or whatever to get all these models up and running and get all the configuration out of the way. And then I can plug into that with my, let's say, my Java application, and I don't need to worry about it, but I can run it, right? And redistribute it. It's going to be the same as what runs in production potentially, so we have the same developer experience.
Right. It makes things a lot easier because we're already using tools. And specifically, some of these tools are our favorites personally, which are known as Podman and Podman Desktop. So this is, as an application developer or an operator, sysadmin, how you can actually build a bootable container. So we're going to use an extension with an application called Podman Desktop. So this is an open source alternative to Docker Desktop. The licensing's open, it's part of the CNCF, so it's governed by this organization. And it makes it simple to go from a container file to build that image and then to export that as a disk image for, say, for example, Amazon or VMware or Anaconda, wherever you actually deploy your systems. We'll actually show this in a live demo here in a second. But using the extension, it's the same thing as, for example, building a traditional application container, but you're pointing to that container file that has the base image, right? And going from there, we can build it for our specific architecture, ARM, x86, wherever we want to go. And then once we have that image, we can then export it as, for example, a .raw or a QCOW2 or one of these different formats for the exact file system by using the same image. So I think that's the really cool part is you build once and then you can deploy that everywhere. And once you have that update, right, we just make a change to the container file, rebuild it, and then push it to the registry.
Right, yeah, especially like the different system architectures too, right? Because like you're working on a Mac here, different architecture than probably what's going to run on a different environment. So yeah.
Right. Yeah, it's magic. Well, we'll see if it's magic. Let's try the demo. What we're going to do is build this as a container application, and then we're going to deploy it as a machine on our local machine here. So the demo you're going to see is this code assistant application. So the first part of this demo is going to be our local, inner loop development as a developer, where we actually are building the application, and then we're going to stick that onto a bootc base image in a container file and build that and deploy that to a system itself in a virtual machine. So, we excited? Ready to see it? Woo! Woo! Yeah! Awesome. Okay, let me hop out of here. As I mentioned before, we're using a tool called Podman, and specifically Podman Desktop. So similar to Docker, you can build, you can run, you can push your images. It's completely open source, so check it out, Podman.
Free.
Yep, free. Woo! So you can see I've got my containers running, and I actually have this ready here. So I'm going to delete it so we can see the magic, and fingers crossed everything works. So in Podman Desktop, there's a lot of different extensions for developers, like think about Minikube or different Red Hat extensions or working with Kubernetes. One of the extensions I have is called the AI Lab, and so
any kind of Docker extension is supported in Podman Desktop as well.
Yeah.
Right? Yeah.
The cool thing about Docker extensions or any of these extensions is they're all running in containers, which is really cool. So think about it. You've got your container engine also running extensions as containers. Very meta. But we'll see how both of these work in a second. So in this extension, I've got different recipes for common use cases. So a lot of us are building out, chatbots or RAG or agentic or code assistants, as we're going to see today. So the idea here is, hey, I've got these repos that I can pull down and build as containers so I can test out these applications. So specifically, the one we're going to use is code generation. So I'll actually show you in VS Code the repository that we're going to be working with. That's cloned locally when we click the start button.
You can make this a little bit bigger again.
That's a great idea. Yeah. So I'll show you quickly what's happening here. Is that we've essentially working with Python. I know you love Python. And we are connecting to a local model on port 8001, right? Checking if it's available. If it is available, we keep a session state. We also have a prompt template here in order to say, hey, you want to help the developer write code. We're going to ask you guys which language that we should try the example in. So, think about that before we open it. And yeah, we just handle the user prompt and the responses. So we have a container file to build this, and we're working with a Python base image, copying in the directory requirements, doing some pip installs, exposing a port, and doing a Streamlit run. So pretty simple, application for a container, right? And what we're going to do here is I'm just going to start this. So I would do, a Docker run or a Podman run after building these containers. And there's different open source models I can use. These are all pulled from Hugging Face, but you could import your own. You could import your own, such as DeepSeek, right? When I come back over here, let's start this recipe. So we're using a model that's IBM Granite, so it's kind of an enterprise type of model that's trained for business tasks, things like that. You're going to see
open source.
Also open source.
Even the weights are open source.
Yes, so that's really important. So you can see that we're built the application and the app is running. We're exposing that port 8501. And we've got our little app running. So remember, this is the application container. We're going to take this and actually deploy it on a system in a little bit. But remember, I was asking you if anyone has a language that they'd like to see this model try to program in.
Is it COBOL?
Oh, Python. My favorite. My favorite. All right, so let's say make a Python banking API. Right, so we send that request, goes to that model in the inference server. All of this is in containers, and we get that response back, right? So this is a cool way to run your own type of copilot or assistant when you're trying to write code. This is pretty good. Don't have time to review it. I'm gonna push it to prod. But what I also want to see is, in the US, all of our systems are COBOL, and much of the world as well. But there's no one who programs in COBOL anymore. So write a example COBOL program. So you can use this to get rich quick because there's no one who can code this anymore, and they're paying a lot of money for these developers. So secret, don't tell anybody I said this. But quick example of working with code generation. But that's cool because it's running in a container right here. So it's actually in a pod. So we've got the infer container, and then we've actually got this Python application in the inference server. What we're going to do now is turn this into a bootable container. So what I have here is this extension that is going to help me take my image and actually export that into whatever qcow2.raw Amazon disk image that we want to use. So when I come back here to the repository, we've actually got the same application, but what we've done is we've containerized this app, pushed it to a registry, and we're going to build out this container file and build this image. So we're starting off with CentOS bootc, so specifically the Stream 9. And remember, it's going to have systemd, it's going to have Podman, it's going to have these basic utilities in addition to the kernel.
And bootc.
And bootc, of course. So we'll copy in our SSH key. We're going to copy in a couple containers. So we're going to copy in this model. This is Mistral, but you could use your favorite coding model or whichever you pick. We're also copying in that image. So the image is what we just saw earlier, that front end that could make the request to the model, and a server. So you could use VLLM, you could use OLlama, Llama C++. And here we're going to copy in a quadlet file. Quadlet file is essentially running a container as a systemd unit so that when we actually boot this system on a virtual machine, it's automatically going to pull those containers and run them on boot. So we don't have to configure anything else. It's just a unit file for systemd, that's really neat, right?
Right. So you can manage your containers in the same way that you manage all your other system things that are running, right?
Right, exactly. Yeah. It makes a lot of sense. We're also going to do these Podman pull commands for each of those containers. So the server, the app, and the model. So let's go ahead and see how this works. So let's see. Can I bring this back up? Awesome. So I'll go ahead and do a makefile. The makefile is just going to kind of build this for us, copy in, what port we want to expose. And when I actually do this, we'll come back over to the container file. we can see all of these steps just kicked off. So we're building this operating system layer by layer, which is super cool. So you can see we did that Podman build command for a specific architecture, copied in those arguments for which containers we want to pull in, add the SSH key, add those images, and then bam.
Yeah, so
build that
very
image.
much the same way as you would create a regular container image, the way that we've been doing for the last 10 years. But this time it's actually for operating system. And from this, we can create an actual image, right? Like
Absolutely.
to actually run on an on a system.
Yeah, that's the magic. So you can see we've built this CodeGen app, and you can see it's highlighted as bootable container enabled. So it is quite big. You're copying in the entire kernel. You're copying in a lot of, specifically for this, an AI model. So the file size is going to be a little bit bigger.
It's not bad if you think about what all is in there.
Right, it's not bad at all. I can push this to a registry, Docker Hub, Key.io, GitHub, for example. But the real magic is, in the last few minutes, I'm going to show you having this here in order to build. So you can see that I can select that container image that's available for building as an operating system. I can select, hey, which disk image type that I want to use, and then I can take that and deploy it locally, for example, or take that somewhere else.
Yep.
Should we show it off?
Let's do it.
Cool. And then one last thing, if you have specific configurations, keys that you need to include in that build, you're able to do that down here. What actually happens in the background when you build this disk image is actually just a podman run command. So you're essentially using what's known as the bootc image builder. So feel free to check that out online and get into the weeds of how to build it for specific architectures. But we're essentially just building for Anaconda for this example. And what's actually going to happen is we're going to build this specific disk image and actually have this, well, if the internet was good, we could kind of show some of the logs, but it's building that file system. It's setting up the configuration to automatically pull those containers. And then if I come over here, let's see if we can see this as an example. I've actually got QEMU. Oh, excuse me. Oh, I had QEMU. It quit.
Live demos, am I right?
Live demos. Let's see if we can get it back open and kind of show how this would actually look. But so I booted and installed the file system, so we have it running. And let's test it out just real quickly. So it's running localhost 192.168. Let's try this 192.168.64.7. Hopefully, okay. Well, I think it might be restarting just because it crashed or something like that. But essentially, you have that ISO. So if I go over here and we go over to images, you can see that I've built this. You have the log, of course, but the ISO in order to install this on your operating system of choice, or maybe if you have Amazon or QCOW2, wherever your application and the operating system need to go, you just install that there. And when you
on a bare metal machine, right?
Bare metal. And once you're in that machine, you go ahead and update that container file. So if I have a new image, I could just say, hey, version 2, right? Rebuild that container file, push that to a registry, and then pull that down into that machine, and you're good to go. So that's kind of the magic of it. But that's the second part where you actually convert to a disk image and deploy that. And once you're ready to update the app, say we want to add a new model or something like that, we can do that there.
Yeah, exactly. Then we can just rebuild the container image, and then we automatically redeploy it using bootc. So it's pretty cool.
It's not bad. Yeah. So cool.
All right.
Well, on that note, guys, it's been an absolute pleasure. I hope you enjoyed the session. I hope you got to see some cool insights. If you want to learn more about the code we used or the slides, please feel free to scan these links. Come up to us. We'd love to talk to you in the booth, talk about open source, AI, and infrastructure. But you guys are awesome. Enjoy the rest of the conference, and thank you for coming.
And we'll be at the booth over there, I think, to answer questions. And there's also a raffle at the end of the day, I heard, at the Red Hat booth for some Ray-Ban Meta sunglasses. So if you want to participate in the raffle, just scan that QR code. And then I think at 6 p.m. they're going to do the raffle, so you have to be there. Must be present to win, but yeah. All right, I'll leave that up for a minute.
Thanks, guys.
Thank you.